A galaxy is a massive, gravitationally bound system consisting of stars, stellar remnants, an interstellar medium of gas and dust, and dark matter, an important but poorly understood component. The word galaxy is derived from the Greek galaxias, literally milky, a reference to the Milky Way. Examples of galaxies range from dwarfs with as few as 10 million stars to giants with 100 trillion stars, each orbiting their galaxy's own center of mass. Galaxies contain varying numbers of planets, star systems, star clusters and types of interstellar clouds. In between these objects is a sparse interstellar medium of gas, dust, and cosmic rays. Supermassive black holes reside at the center of most galaxies. They are thought to be the primary driver of active galactic nuclei found at the core of some galaxies. The Milky Way galaxy is known to harbor at least one such object. Galaxies have been historically categorized according to their apparent shape, usually referred to as their visual morphology. A common form is the elliptical galaxy, which is an ellipse-shaped light profile. Spiral galaxies are disc-shaped with dusty, curving arms. Those with irregular or unusual shapes are known as irregular galaxies and typically originate from disruption by the gravitational pull of neighboring galaxies. Such interactions between nearby galaxies, which may ultimately result in a merger, sometimes induce significantly increased incidence of star formation leading to starburst galaxies. There are probably more than 170 billion galaxies in the observable universe. Most are 1,000 to 100,000 pascs in diameter and usually separated by distances on the order of millions of pascs. Intergalactic space is filled with a tenuous gas of an average density less than 1 atom per cubic meter. The majority of galaxies are organized into a neither fully random nor fully deterministic set of associations known as galaxy groups and clusters, which, in turn usually form larger superclusters. At the largest scale, these associations are generally arranged into sheets and filaments, which are surrounded by immense voids. Etymology. The word galaxy derives from the Greek term for our own galaxy, galaxias, or kykelos galacticos for its appearance as a lighter-colored band in the sky. In Greek mythology, Zeus places his son born by a mortal woman, the infant Heracles, on Hera's breast while she is asleep so that the baby will drink her divine milk and will thus become immortal. Hera wakes up while breastfeeding and then realizes she is nursing an unknown baby. She pushes the baby away and a jet of her milk sprays the night sky, producing the faint band of light known as the Milky Way. In the astronomical literature, the capitalized word galaxy is used to refer to our galaxy, the Milky Way, to distinguish it from the billions of other galaxies. The English term Milky Way can be traced back to a story by Chaucer. See yonder, lo, the Galaxia, a which men clepeth the Milky Way, for it is white. When William Herschel constructed his catalogue of deep sky objects in 1786, he used the name spiral nebula for certain objects such as M31. These would later be recognized as immense conglomerations of stars, when the true distance to these objects began to be appreciated, and they would be termed island universes. However, the word universe was understood to mean the entirety of existence, so this expression fell into disuse and the objects instead became known as galaxies. Nomenclature. Tens of thousands of these galaxies have now been catalogued. Only a few have been given a well-established name, such as the Andromeda Galaxy, the Magellanic Clouds, the Whirlpool Galaxy and the Sombrero Galaxy. Astronomers work with numbers from certain catalogues, such as the Messier catalogue, the NGC, the IC, the CGCG, the MCG and UGC. All of the well-known galaxies appear in one or more of these catalogues but each time under a different number. For example, the Messier 109, a spiral system which has the number 109 in the catalogue of Messier also codes NCG 3992, UGC 6937, CGCG 269-023, MCG plus 09-20-044 and PGC 37617. Because it is customary in science to assign names to most of the studied objects, even to the smallest ones, The Belgian astrophysicist Gerard Bodevier and the classicist Michel Berger started a new catalogue in which 1,000 of well-known galaxies are given meaningful, descriptive names in Latin in accordance with the binomial nomenclature that one uses in other sciences such as biology, anatomy, paleontology and in other fields of astronomy such as the geography of Mars. One of the arguments to do so is that these impressive objects deserve better than uninspired codes. For instance, Bodevier and Berger proposed the informal, descriptive name Corlomorphus Ursae Majoris for the well-formed barred galaxy Messier 109 in Ursa Major. Observation history, the realization that we live in a galaxy, and that there were, in fact, many other galaxies, parallels discoveries that were made about the Milky Way and other nebulae in the night sky. Milky Way. The Greek philosopher Democritus proposed that the bright band on the night sky known as the Milky Way might consist of distant stars. Aristotle, however, believed the Milky Way to be caused by the ignition of the fiery exhalation of some stars that were large, numerous and close together, and that the ignition takes place in the upper part of the atmosphere, in the region of the world that is continuous with the heavenly motions. The Neoplatonist philosopher Olympiodorus the Younger was scientifically critical of this view, arguing that if the Milky Way was sublunary it should appear different at different times and places on Earth, and that it should have parallax, which it does not. In his view, the Milky Way was celestial. This idea would be influential later in the Islamic world. According to Mu'ani Muhammad, the Arabian astronomer Al-Hazen made the first attempt at observing and measuring the Milky Way's parallax, and he thus determined that because the Milky Way had no parallax, it was very remote from the Earth and did not belong to the atmosphere. The Persian astronomer Al-Barani proposed the Milky Way galaxy to be a collection of countless fragments of the nature of nebulous stars. The Andalusian astronomer Ibn Bajor proposed that the Milky Way was made up of many stars that almost touch one another and appear to be a continuous image due to the effect of refraction from sublunary material, citing his observation of the conjunction of Jupiter and Mars as evidence of this occurring when two objects are near. In the 14th century, the Syrian-born Ibn Qayyim proposed the Milky Way galaxy to be a myriad of tiny stars packed together in the sphere of the fixed stars. Actual proof of the Milky Way consisting of many stars came in 1610 when the Italian astronomer Galileo Galilei used a telescope to study the Milky Way and discovered that it is composed of a huge number of faint stars. In 1750 the English astronomer Thomas Wright, in his An Original Theory or New Hypothesis of the Universe, speculated that the galaxy might be a rotating body of a huge number of stars held together by gravitational forces, akin to the Solar System but on a much larger scale. The resulting disk of stars can be seen as a band on the sky from our perspective inside the disk. In a treatise in 1755, Immanuel Kant elaborated on Wright's idea about the structure of the Milky Way. The first attempt to describe the shape of the Milky Way and the position of the Sun in it was carried out by William Herschel in 1785 by carefully counting the number of stars in different regions of the sky. He produced a diagram of the shape of the galaxy with the Solar System close to the center. Using a refined approach, Kapteyn in 1920 arrived at the picture of a small ellipsoid galaxy with the Sun close to the center. A different method by Harlow Shapley based on the cataloguing of globular clusters led to a radically different picture, a flat disk with diameter approximately 70 kilopascs and the Sun far from the center. Both analyses failed to take into account the absorption of light by interstellar dust present in the galactic plane, but after Robert Julius Trumpeter quantified this effect in 1930 by studying open clusters, the present picture of our host galaxy, the Milky Way, emerged. Distinction from other nebulae. In the 10th century, the Persian astronomer al-Sufi made the earliest recorded observation of the Andromeda galaxy, describing it as a small cloud. Al-Sufi, who published his findings in his Book of Fixed Stars in 964, also identified the large Magellanic Cloud, which is visible from Yemen, though not from Isfahan. It was not seen by Europeans until Magellan's voyage in the 16th century. The Andromeda Galaxy was independently rediscovered by Simon Marius in 1612. These are the only galaxies outside the Milky Way that are easily visible to the unaided eye, so they were the first galaxies to be observed from Earth. In 1750 Thomas Wright, in his original theory or new hypothesis of the universe, speculated that the Milky Way was a flattened disk of stars, and that some of the nebulae visible in the night sky might be separate Milky Ways. In 1755, Immanuel Kant used the term island universe to describe these distant nebulae. Toward the end of the 18th century, Charles Messier compiled a catalogue containing the 109 brightest nebulae, later followed by a larger catalogue of 5,000 nebulae assembled by William Herschel. In 1845, Lord Rosse constructed a new telescope and was able to distinguish between elliptical and spiral nebulae. He also managed to make out individual point sources in some of these nebulae, lending credence to Kant's earlier conjecture. In 1912, Vesto Slipher made spectrographic studies of the brightest spiral nebulae to determine if they were made from chemicals that would be expected in a planetary system. However, Slipher discovered that the spiral nebulae had high redshifts, indicating that they were moving away at a rate higher than the Milky Way's escape velocity. Thus they were not gravitationally bound to the Milky Way, and were unlikely to be a part of the galaxy. In 1917, Heber Curtis had observed a nova S Andromedae within the Great Andromeda Nebula. Searching the photographic record, he found 11 more novae. Curtis noticed that these novae were, on average, 10 magnitudes fainter than those that occurred within our galaxy. As a result, he was able to come up with a distance estimate of 150,000 arcsec. He became a proponent of the so-called island universes hypothesis, which holds that spiral nebulae are actually independent galaxies. In 1920, the so-called Great Debate took place between Harlow Shapley and Heber Curtis, concerning the nature of the Milky Way, spiral nebulae, and the dimensions of the universe. To support his claim that the Great Andromeda Nebula was an external galaxy, Curtis noted the appearance of dark lanes resembling the dust clouds in the Milky Way, as well as the significant Doppler shift. The matter was conclusively settled in the early 1920s. In 1922, the Estonian astronomer Ernst Pick gave a distance determination that supported the theory that the Andromeda Nebula is indeed a distant extragalactic object. Using the new 100-inch Mount Wilson telescope, Edwin Hubble was able to resolve the outer parts of some spiral nebulae as collections of individual stars and identified some Cepheid variables, thus allowing him to estimate the distance to the nebulae. They were far too distant to be part of the Milky Way. In 1936, Hubble produced a classification system for galaxies that is used to this day, the Hubble sequence. Modern research. In 1944, Hendrik van der Hulst predicted microwave radiation at a wavelength of 21 cm resulting from interstellar atomic hydrogen gas. This radiation was observed in 1951. The radiation allowed for much improved study of the Milky Way galaxy, since it is not affected by dust absorption and its Doppler shift can be used to map the motion of the gas in the galaxy. These observations led to the postulation of a rotating bar structure in the center of the galaxy. With improved radio telescopes, hydrogen gas could also be traced in other galaxies. In the 1970s it was discovered in Vera Rubin's study of the rotation speed of gas in galaxies that the total visible mass does not properly account for the speed of the rotating gas. This galaxy rotation problem is thought to be explained by the presence of large quantities of unseen dark matter. Beginning in the 1990s, the Hubble Space Telescope yielded improved observations. Among other things, it established that the missing dark matter in our galaxy cannot solely consist of inherently faint and small stars. The Hubble Deep Field, an extremely long exposure of a relatively empty part of the sky, provided evidence that there are about 125 billion galaxies in the universe. Improved technology in detecting the spectra invisible to humans allowed detection of other galaxies that are not detected by Hubble. Particularly, galaxy surveys in the zone of avoidance have revealed a number of new galaxies. Types and morphology. Galaxies come in three main types: ellipticals, spirals, and irregulars. A slightly more extensive description of galaxy types based on their appearance is given by the Hubble sequence. Since the Hubble sequence is entirely based upon visual morphological type, it may miss certain important characteristics of galaxies such as star formation rate and activity in the core. Ellipticals. The Hubble classification system rates elliptical galaxies on the basis of their ellipticity, ranging from E0, being nearly spherical, up to E7, which is highly elongated. These galaxies have an ellipsoidal profile, giving them an elliptical appearance regardless of the viewing angle. Their appearance shows little structure and they typically have relatively little interstellar matter. Consequently, these galaxies also have a low portion of open clusters and a reduced rate of new star formation. Instead, they are dominated by generally older, more evolved stars that are orbiting the common center of gravity in random directions. The stars contain low abundances of heavy elements because star formation ceases after the initial burst. In this sense, they have some similarity to the much smaller globular clusters. The largest galaxies are giant ellipticals. Many elliptical galaxies are believed to form due to the interaction of galaxies, resulting in a collision and merger. They can grow to enormous sizes, and giant elliptical galaxies are often found near the core of large galaxy clusters. Starburst galaxies are the result of such a galactic collision that can result in the formation of an elliptical galaxy. Spirals. Spiral galaxies are galaxies whose visible stars take on a spiraling pinwheel shape. Though the stars and other visible material contained in such a galaxy lie mostly on a plane, the majority of mass in spiral galaxies exists in a roughly spherical halo of dark matter that extends beyond the visible component. Spiral galaxies consist of a rotating disk of stars and interstellar medium, along with a central bulge of generally older stars. Extending outward from the bulge are relatively bright arms. In the Hubble classification scheme, spiral galaxies are listed as type S, followed by a letter that indicates the degree of tightness of the spiral arms and the size of the central bulge. An SR galaxy has tightly wound, poorly defined arms and possesses a relatively large core region. At the other extreme, an SC galaxy has open, well-defined arms and a small core region. A galaxy with poorly defined arms is sometimes referred to as a flocculent spiral galaxy. In contrast to the grand design spiral galaxy that has prominent and well-defined spiral arms. It appears the reason that some spiral galaxies are fat and bulging while some are flat disks is because of how fast they rotate. In spiral galaxies, the spiral arms do have the shape of approximate logarithmic spirals, a pattern that can be theoretically shown to result from a disturbance in a uniformly rotating mass of stars. Like the stars, the spiral arms rotate around the center, but they do so with constant angular velocity. The spiral arms are thought to be areas of high-density matter, or density waves. As stars move through an arm, the space velocity of each stellar system is modified by the gravitational force of the higher density. This effect is akin to a wave of slowdowns moving along a highway full of moving cars. The arms are visible because the high density facilitates star formation, and therefore they harbor many bright and young stars. A majority of spiral galaxies, including our own Milky Way galaxy, have a linear, bar-shaped band of stars that extends outward to either side of the core, then merges into the spiral arm structure. In the Hubble classification scheme, these are designated by an SB, followed by a lowercase letter that indicates the form of the spiral arms. Bars are thought to be temporary structures that can occur as a result of a density wave radiating outward from the core, or else due to a tidal interaction with another galaxy. Many barred spiral galaxies are active, possibly as a result of gas being channeled into the core along the arms. Our own galaxy, the Milky Way, is a large disc-shaped barred spiral galaxy about 30 kilopascs in diameter and a kilopasc thick. It contains about 200 billion stars and has a total mass of about 600 billion times the mass of the Sun. Other morphologies: peculiar galaxies are galactic formations that develop unusual properties due to tidal interactions with other galaxies. An example of this is the Ring Galaxy, which possesses a ring-like structure of stars and interstellar medium surrounding a bare core. A ring galaxy is thought to occur when a smaller galaxy passes through the core of a spiral galaxy. Such an event may have affected the Andromeda Galaxy, as it displays a multi-ring-like structure when viewed in infrared radiation. A lenticular galaxy is an intermediate form that has properties of both elliptical and spiral galaxies. These are categorized as Hubble-type SO, and they possess ill-defined spiral arms with an elliptical halo of stars. In addition to the classifications mentioned above, there are a number of galaxies that cannot be readily classified into an elliptical or spiral morphology. These are categorized as irregular galaxies. An IRI galaxy has some structure but does not align cleanly with the Hubble classification scheme. IRI galaxies do not possess any structure that resembles the Hubble classification, and may have been disrupted. Nearby examples of irregular galaxies include the Magellanic Clouds. Dwarfs. Despite the prominence of large elliptical and spiral galaxies, most galaxies in the universe appear to be dwarf galaxies. These galaxies are relatively small when compared with other galactic formations, being about 1/100th the size of the Milky Way, containing only a few billion stars. Ultra-compact dwarf galaxies have recently been discovered that are only 100 parsecs across. Many dwarf galaxies may orbit a single larger galaxy. The Milky Way has at least a dozen such satellites, with an estimated 300-500 yet to be discovered. Dwarf galaxies may also be classified as elliptical, spiral, or irregular. Since small dwarf ellipticals bear little resemblance to large ellipticals, they are often called dwarf spheroidal galaxies instead. A study of 27 Milky Way neighbors found that in all dwarf galaxies, the central mass is approximately 10 million solar masses, regardless of whether the galaxy has thousands or millions of stars. This has led to the suggestion that galaxies are largely formed by dark matter, and that the minimum size may indicate a form of warm dark matter incapable of gravitational coalescence on a smaller scale. Unusual dynamics and activities, interacting. Interactions between these galaxies are relatively frequent, and play an important role in their evolution. Near misses between galaxies result in warping distortions due to tidal interactions, and may cause some exchange of gas and dust. Collisions occur when two galaxies pass directly through each other and have sufficient relative momentum not to merge. The stars within these interacting galaxies will typically pass straight through without colliding. However, the gas and dust within the two forms will interact. This can trigger bursts of star formation as the interstellar medium becomes disrupted and compressed. A collision can severely distort the shape of one or both galaxies, forming bars, rings or tail-like structures. At the extreme of interactions are galactic mergers. In this case the relative momentum of the two galaxies is insufficient to allow the galaxies to pass through each other. Instead, they gradually merge to form a single, larger galaxy. Mergers can result in significant changes to morphology, as compared to the original galaxies. In the case where one of the galaxies is much more massive, however, the result is known as cannibalism. In this case the larger galaxy will remain relatively undisturbed by the merger, while the smaller galaxy is torn apart. The Milky Way galaxy is currently in the process of cannibalizing the Sagittarius dwarf elliptical galaxy and the Canis major dwarf galaxy. Starburst. Stars are created within galaxies from a reserve of cold gas that forms into giant molecular clouds. Some galaxies have been observed to form stars at an exceptional rate, known as a starburst. Should they continue to do so, however, they would consume their reserve of gas in a time frame lower than the lifespan of the galaxy. Hence starburst activity usually lasts for only about 10 million years, a relatively brief period in the history of a galaxy. Starburst galaxies were more common during the early history of the universe, and, at present, still contribute an estimated 15% to the total star production rate. Starburst galaxies are characterized by dusty concentrations of gas and the appearance of newly formed stars, including massive stars that ionize the surrounding clouds to create H2 regions. These massive stars produce supernovae explosions, resulting in expanding remnants that interact powerfully with the surrounding gas. These outbursts trigger a chain reaction of star building that spreads throughout the gaseous region. Only when the available gas is nearly consumed or dispersed does the starburst activity come to an end. Starbursts are often associated with merging or interacting galaxies. The prototype example of such a starburst-forming interaction is M82, which experienced a close encounter with the larger M81. Irregular galaxies often exhibit space knots of starburst activity. Active nucleus. A portion of the galaxies we can observe are classified as active. That is, a significant portion of the total energy output from the galaxy is emitted by a source other than the stars, dust and interstellar medium. The standard model for an active galactic nucleus is based upon an accretion disk that forms around a supermassive black hole at the core region. The radiation from an active galactic nucleus results from the gravitational energy of matter as it falls toward the black hole from the disk. In about 10% of these objects, a diametrically opposed pair of energetic jets ejects particles from the core at velocities close to the speed of light. The mechanism for producing these jets is still not well understood. Active galaxies that emit high-energy radiation in the form of X-rays are classified as Seyfert galaxies or quasars, depending on the luminosity. Blazes are believed to be an active galaxy with a relativistic jet that is pointed in the direction of Earth. A radio galaxy emits radio frequencies from relativistic jets. A unified model of these types of active galaxies explains their differences based on the viewing angle of the observer. Possibly related to active galactic nuclei are low ionization nuclear emission line regions. The emission from liner-type galaxies is dominated by weakly ionized elements. Approximately one-third of nearby galaxies are classified as containing liner nuclei. Formation and evolution. The study of galactic formation and evolution attempts to answer questions regarding how galaxies formed and their evolutionary path over the history of the universe. Some theories in this field have now become widely accepted, but it is still an active area in astrophysics. Formation. Current cosmological models of the early universe are based on the Big Bang theory. About 300,000 years after this event, atoms of hydrogen and helium began to form, in an event called recombination. Nearly all the hydrogen was neutral and readily absorbed light, and no stars had yet formed. As a result, this period has been called the Dark Ages. It was from density fluctuations in this primordial matter that larger structures began to appear. As a result, masses of baryonic matter started to condense within cold dark matter halos. These primordial structures would eventually become the galaxies we see today. Evidence for the early appearance of galaxies was found in 2006, when it was discovered that the galaxy IOK-1 has an unusually high redshift of 6.96, corresponding to just 750 million years after the Big Bang and making it the most distant and primordial galaxy yet seen. While some scientists have claimed other objects have higher redshifts, IOK-1's age and composition have been more reliably established. However, in December 2012, astronomers reported that the UDF J39546284 galaxy is the most distant galaxy known and has a redshift value of 11.9. The galaxy, estimated to have existed around 380 million years after the Big Bang, is about 13.42 billion light-years away. The existence of such early protogalaxies suggests that they must have grown in the so-called Dark Ages. The detailed process by which such early galaxy formation occurred is a major open question in astronomy. Theories could be divided into two categories, top-down and bottom-up. In top-down theories, protogalaxies form in a large-scale simultaneous collapse lasting about 100 million years. In bottom-up theories, small structures such as globular clusters form first, and then a number of such bodies accrete to form a larger galaxy. Once protogalaxies began to form and contract, the first halo stars appeared within them. These were composed almost entirely of hydrogen and helium, and may have been massive. If so, these huge stars would have quickly consumed their supply of fuel and became supernovae, releasing heavy elements into the interstellar medium. This first generation of stars reionized the surrounding neutral hydrogen, creating expanding bubbles of space through which light could readily travel. Evolution. Within a billion years of a galaxy's formation, key structures begin to appear. Globular clusters, the central supermassive black hole, and a galactic bulge of metal poor population II stars form. the creation of a supermassive black hole appears to play a key role in actively regulating the growth of galaxies by limiting the total amount of additional matter added. During this early epoch, galaxies undergo a major burst of star formation. During the following 2 billion years, the accumulated matter settles into a galactic disk. A galaxy will continue to absorb infalling material from high-velocity clouds and dwarf galaxies throughout its life. This matter is mostly hydrogen and helium. The cycle of stellar birth and death slowly increases the abundance of heavy elements, eventually allowing the formation of planets. The evolution of galaxies can be significantly affected by interactions and collisions. Mergers of galaxies were common during the early epoch, and the majority of galaxies were peculiar in morphology. Given the distances between the stars, the great majority of stellar systems and colliding galaxies will be unaffected. However, gravitational stripping of the interstellar gas and dust that makes up the spiral arms produces a long train of stars known as tidal tails. Examples of these formations can be seen in NGC 4676 or the Antennae galaxies. As an example of such an interaction, the Milky Way galaxy and the nearby Andromeda galaxy are moving toward each other at about 130 km per second, and depending upon the lateral movement the two may collide in about 5 to 6 billion years. Although the Milky Way has never collided with a galaxy as large as Andromeda before, evidence of past collisions of the Milky Way with smaller dwarf galaxies is increasing. Such large-scale interactions are rare. As time passes, mergers of two systems of equal size become less common. Most bright galaxies have remained fundamentally unchanged for the last few billion years, and the net rate of star formation probably also peaked approximately 10 billion years ago. Future trends: at present, most star formation occurs in smaller galaxies where cool gas is not so depleted. Spiral galaxies, like the Milky Way, only produce new generations of stars as long as they have dense molecular clouds of interstellar hydrogen in their spiral arms. Elliptical galaxies are already largely devoid of this gas, and so form no new stars. The supply of star-forming material is finite. Once stars have converted the available supply of hydrogen into heavier elements, new star formation will come to an end. The current era of star formation is expected to continue for up to 100 billion years, and then the stellar age will wind down after about 10 trillion to 100 trillion years, as the smallest, longest-lived stars in our astrosphere, tiny red dwarfs, begin to fade. At the end of the stellar age, galaxies will be composed of compact objects, brown dwarfs, white dwarfs that are cooling or cold, neutron stars, and black holes. Eventually, as a result of gravitational relaxation, all stars will either fall into central supermassive black holes or be flung into intergalactic space as a result of collisions. Larger-scale structures. Deep sky surveys show that galaxies are often found in relatively close association with other galaxies. Solitary galaxies that have not significantly interacted with another galaxy of comparable mass during the past billion years are relatively scarce. Only about 5% of the galaxies surveyed have been found to be truly isolated. However, these isolated formations may have interacted and even merged with other galaxies in the past, and may still be orbited by smaller, satellite galaxies. Isolated galaxies can produce stars at a higher rate than normal, as their gas is not being stripped by other nearby galaxies. On the largest scale, the universe is continually expanding, resulting in an average increase in the separation between individual galaxies. Associations of galaxies can overcome this expansion on a local scale through their mutual gravitational attraction. These associations formed early in the universe, as clumps of dark matter pulled their respective galaxies together. Nearby groups later merged to form larger-scale clusters. This ongoing merger process heats the intergalactic gas within a cluster to very high temperatures, reaching 30–100 megakelvins. About 70–80% of the mass in a cluster is in the form of dark matter, with 10–30% consisting of this heated gas and the remaining few percent of the matter in the form of galaxies. Most galaxies in the universe are gravitationally bound to a number of other galaxies. These form a fractal-like hierarchy of clustered structures, with the smallest such associations being termed groups. A group of galaxies is the most common type of galactic cluster, and these formations contain a majority of the galaxies in the universe. To remain gravitationally bound to such a group, each member galaxy must have a sufficiently low velocity to prevent it from escaping. If there is insufficient kinetic energy, however, the group may evolve into a smaller number of galaxies through mergers. Larger structures containing many thousands of galaxies packed into an area a few megapascals across are called clusters. Clusters of galaxies are often dominated by a single giant elliptical galaxy, known as the brightest cluster galaxy, which, over time, tidally destroys its satellite galaxies and adds their mass to its own. Superclusters contain tens of thousands of galaxies, which are found in clusters, groups and sometimes individually. At the supercluster scale, galaxies are arranged into sheets and filaments surrounding vast empty voids. Above this scale, the universe appears to be the same in all directions. The Milky Way galaxy is a member of an association named the Local Group, a relatively small group of galaxies that has a diameter of approximately only a megapascal. The Milky Way and the Andromeda Galaxy are the two brightest galaxies within the group. Many of the other member galaxies are dwarf companions of these two galaxies. The Local Group itself is a part of a cloud-like structure within the Virgo supercluster, a large, extended structure of groups and clusters of galaxies centered on the Virgo cluster. And the Virgo supercluster itself is a part of the Pisces Settlers supercluster complex, a giant galaxy filament. Multi-wavelength observation. After galaxies external to the Milky Way were found to exist, initial observations were made mostly using visible light. The peak radiation of most stars lies here, so the observation of the stars that form galaxies has been a major component of optical astronomy. It is also a favorable portion of the spectrum for observing ionized H2 regions, and for examining the distribution of dusty arms. The dust present in the interstellar medium is opaque to visual light. It is more transparent to far infrared, which can be used to observe the interior regions of giant molecular clouds and galactic cores in great detail. Infrared is also used to observe distant, red-shifted galaxies that were formed much earlier in the history of the universe. Water vapor and carbon dioxide absorb a number of useful portions of the infrared spectrum, so high-altitude or space-based telescopes are used for infrared astronomy. The first non-visual study of galaxies, particularly active galaxies, was made using radio frequencies. The atmosphere is nearly transparent to radio between 5 MHz and 30 GHz. Large radio interferometers have been used to map the active jets emitted from active nuclei. Radio telescopes can also be used to observe neutral hydrogen, including, potentially, the non-ionized matter in the early universe that later collapsed to form galaxies. Ultraviolet and X-ray telescopes can observe highly energetic galactic phenomena. An ultraviolet flare was observed when a star in a distant galaxy was torn apart from the tidal forces of a black hole. The distribution of hot gas in galactic clusters can be mapped by X-rays. The existence of supermassive black holes at the cores of galaxies was confirmed through X-ray astronomy. See also: Notes. References. Bibliography. External links: Galaxies on In Our Time at the BBC. Galaxies, SEDS Messier Pages, An Atlas of the Universe, Galaxias Information and Amateur Observations, The Oldest Galaxy Yet Found, Galaxy Classification Project, Harnessing the Power of the Internet and the Human Brain, How Many Galaxies Are in Our Universe? The Most Beautiful Galaxies on Astronew, 3D video over a million galaxies of billions of stars equal Berkeley Lab animated.